we will start a little later when everyone will hopefully show up. I'm sure you are missing one. Remember, it doesn't serve well. I may have already distributed this printouts before. Organized. Keep sitting. I like.
Hello?
To have a little exercise. But thank you. This is the best.
God.
Oh.
Yeah, everybody. Other than we are. Hello.
Okay.
Yeah.
Okay.
I don't know. Yeah, he can. We're in the wrong class.
That's good. That's good.
That's good. We can head to Yemen. It's right here, no?
No, it's the block.
So it
No, it's
is.
just
It is
opposite.
Memorial.
Mehdi
Yeah,
and Anas, right?
Yeah, Kinito.
Okay. So you're sitting behind one terminal?
Yeah, but the class is happening at EML 170.
Yes.
Okay, we can be there, no? We'll go there.
Yeah.
Yeah, we can be there. We can be there. Okay.
Okay. There are undergraduates have light overlap, so they will probably also come in like a couple of minutes.
Right. Okay.
So let me know if you need connection and if you want to do the same as this gentleman do. It's probably a little preferred to be in class, but there are facilities to participate even if we're traveling. I'll probably will be traveling to conferences, but not cancel the class. But delivering it remotely. Do you have in mind projects for the end of this semester for this class, or you're still thinking?
I'm still thinking.
I'm probably gonna do something with my nanowire, but I don't know specifically what yet.
Okay, so you have you faced challenges that it doesn't converge.
Yeah, it's converging extremely slowly right now.
Do you have plan B?
Plan B? No, but I could think of something.
Like how many unit cells is across the nanowire?
Well, it's just 1 unit, so
If you do not do doping, if you do pure silicon,
pure silicon.
yeah,
Um,
then it will be like 6 or 8 unit cells.
I'm not sure off the top of my head.
You can check and maybe try to do like 1 unit cells between this metal and check if it converges, just as a plan B, not as a primary target.
Yeah.
And you did try to optimize the size of the cell and use K-means.
Right now I'm letting it change the size.
Yeah, there is no rush, spend assigned time to select projects and discuss. Semester is short, but it is a pretty sufficient time to complete. Hi Mary, how are you?
Good.
Hey, we are waiting for a couple of people to come in person. We'll start soon. But recording, we are already on recordings, and it can be used as a commercial advertisement of NDSU facilities, where everyone connects from outside. Do you have in mind specific project for your like for the end of semester, or you are debating?
Can you hear me?
Yes.
Okay. So I have a couple of projects in mind. I'm wanting to work on different small quantum dots, different size, lots of material, and I'm working with Dr. Razlo's postdoc from Poland, and she assigned me this as she's interested in the semiconducting properties of these small clusters. And first it started out with silver, solenoid, silver sulfur structures, so like a couple metals and then a non-metal in there. And another one is going to be a little bit different, is I'd like to work on the macro size scale of a polymer where it's in vacuum and then we subject it to water, or if we add other interesting moieties to it to see and look at the structure property relationships. So those are I want to work on 2 projects, and they're both related to research.
Good. Good to know. Thank you. So I'll probably start slowly from recalling what we did before, and if someone will come later, then we'll start new material. So what's the name of the cat?
This is Hypatia.
How?
Hypatia, yeah.
Hypatia.
It's Hypatia. She's named after the Greek mathematician.
Okay.
So she's a sweetheart. So yeah.
That's great. So we've seen these slides many times, and so we are trying to populate and I'm trying to add the recordings of what we are doing here, but there are two new things. So there will be labs at the bottom, and here is the link that you can use if you don't feel comfortable coming in class.
Hello.
Oh, yes, super quick.
Maybe it's here.
Thanks for coming. So there is a little homework. That it's not super important, but I thought you were just missing homeworks. You are so bored, you need some entertainment. So you can write in the equation for non-diabatic coupling in plain terms, so that later on you can use it in your papers, so that you know what you're doing. Give some examples of oh, yes. 1, 2, 3. For potential energy surfaces. And what else? Give limitations when potential energy surfaces are not applicable. Also, I think everything again can be done in 15 minutes, although it was lots of handwriting. You can go to Google Images, type the word potential energy surfaces, and just put it in PowerPoint as an example, and maybe give a comment like, I like it. Here is the minimum. Here is the barrier. Here is the like. If you want to, just some. Going over the concept so that later on you can confidently use it. Here are your the things that you volunteered to present. So it will be literally in 1 week from now.
Yes.
And maybe Kurt, you do not have classes back to back.
Not on this late.
No, because Cage and who else? And Ben, they have class back to back, and therefore they will start in time. So here are a couple of printouts that you do not need to read anything. You can just use them as your fireplace, but it is. Complementary to what we are discussing in class, and maybe it is different words. So you see that there is a diversity of ways how things are presented. And at the very beginning, Mary was asking which book is the best. There is no the best. Each of them show different angle, and by looking simultaneously you crystallize your own thoughts. So because it is a rather young discipline, there are no super preferred text that contains everything. And you may enjoy this diversity of descriptions. Right? The last one is more advanced and complicated and complete. But if it looks, if like I do not have steam, or I'll roll back to something simpler. So they go over similar concepts. So what we did before, we are going over the theories behind the software that allows to compute the properties for certain structures. And we did formulate molecular Schrödinger equation and realized that it is too big for any modern computation, right? Therefore, we decided to follow steps of Born and Oppenheimer to at least separate nuclear degree of freedom and electronic degree of freedom, right? And we identified three terms in the molecular Hamiltonian that relate to electronic part, found their eigenstates, and then used superposition of these eigenstates as trial solution to solve overall molecular Schrödinger equation. And in this trial solution, the expansion coefficients are unknown. At the same time, they are these expansion coefficients are the unknown nuclear wave functions. When we did complete this operation, I'm not showing because probably you're tired of me repeating the same things again and again. After we already got rid of the electronic wave functions, there are four terms. These last three terms look very much like Schrödinger equation for nuclear wave function. R capital is for nuclei. And the first term includes some strange things that we may want to remove for simplicity. So main thing that is present there is so-called non-adiabatic coupling, which is response of electronic wave functions to change in position of nuclei times nuclear momentum. If momentum is zero, if there is no temperature and no motion, then these strange terms are disabled, and everything works fine. So the non-adiabatic couplings contribute to transitions between potential energy surfaces, right? And they originate from kinetic energy of nucleus, which has three terms, two for non-adiabatic coupling and one for pure nuclear kinetic energy. So if we are at relatively low temperature, relatively low momenta of each ions, we remove just by our free will, by decision, as an approximation, we remove non-adiabatic couplings, and then we do have what? Schrödinger equation, time-dependent Schrödinger equation, time-independent time-independent Schrödinger equation for nuclear wave function, right? What? And we are not happy at this step yet. We are not happy because even if we did remove non-adiabatic couplings, it doesn't. We decoupled to some extent electronic and nuclear degrees of freedom, and but it is not complete independence. The electronic levels of electronic states do depend on positions of nuclei, and forces between nuclei do depend on electronic state, in which of eigenstates or superposition of eigenstates we are, right? So those are a couple of things. And if you believe this, so we came to a situation when we have two time-independent Schrödinger equation, one for electronic degrees of freedom, another is for nuclear degrees of freedom. And there is a little discomfort in a sense that nuclei are moving, and it is better to have time-dependent Schrödinger equation. So what we did last time, we took the everything that we can identify as Hamiltonian for nuclear degrees of freedom and constructed time-dependent Schrödinger equation, right? Okay. And then we are referring back to our kindergarten time when we were solving time-dependent Schrödinger equation every hour, or just believing that if you start, for time-dependent Schrödinger equation, you do need initial condition, right?
Were you talking for that rabbit, or you said the kindergarten thing? Was that the rabbit thing you were talking about?
No, not the rabbit,
No?
not the rabbit.
Okay.
The important part of our class, Gage and Ben didn't arrive yet, but they had their kindergarten PChem last semester when they were practicing to run wave packet dynamics several times. So when you do have potential, right, and you solve, you need, in addition to Hamiltonian potential, you also need initial condition. And typical initial condition for nuclear wave functions is Gaussian distribution around the center, right? And argument of this nuclear wave functions is positions, or better, one can formulate it in terms of interatomic positions, or like center them at the equilibrium distances. And you can set up initial conditions as like little Gaussian distributions near the equilibrium, but you do not need to have them literally at the equilibrium. You can start a little away, or at the equilibrium but with non-zero momentum. And then these wave packet distributions, after you solve equations, start moving forth and back. Okay? This is cool, but too expensive. For all nuclei except hydrogen, proton, quantum effects are, I wouldn't say they do not exist, but we can survive by neglecting them, or like taking them as a correction at a later time. When do you need quantum nuclear effects? In which experiment? Example.
What do you need all at all?
Which experiment that people do in characterization of materials on the routine basis demonstrate quantum properties of nuclei? It's one of the spectroscopies.
We're still learning.
Me too.
Nuclear magnetic resonance.
No, in nuclear magnetic resonance, it is a microwave radio frequency, right? And nuclei are not moving, change.
Laser?
Huh?
Laser?
In some lasers it is important, but it's there are more bright manifestations. So Stokes shift in molecular spectroscopy for microscopy, and there is even brighter, the Raman scattering. Did you hear about it? Right? So the Raman scattering, the signal is offset by number of by vibrational frequency multiplied, which has to be quantized. Right? There are multiples of those. But if you don't describe Raman, you can forget it. So the idea that we do not need the nuclear, well, we can neglect fine, tiny details of nuclear wave packet propagation. Instead, it would be really nice to focus on a average position of each internuclear distance and treat them as point charges. So forget about quantum mechanics for nuclear degrees of freedom, in a sense that we do not, in a sense of expanse of calculations, so that we will not solve quantum equations. We are not abandoning, we are not telling that there are no quantum effects. We take them partially into account while we derive equations. And then we do limiting case. So we already discussed it last time, right? And I will provide some details. Again, do not concentrate, lean back, relax. I'll give you a signal when to focus. And as I promised, things will go less and less complicated, more and more simple. So this little illustration is how Gaussian wave packet looks like. So the envelope function looks like a hump of a camel, but inside wave function may oscillate and have real and imaginary part, especially if it has momentum. But what we need is only to know the center and maybe the momentum, and that's it. So we already mentioned that we do have permission to do so from Ehrenfest, right? So I'm going, if you do not care about Ehrenfest, just relax. It will be only details about this transition, additional details about transition from quantum nuclear part to more like classical. Okay. Sometimes what I'm talking and what is shown is diverging, but we are going in different spaces. Here is time independent Schrödinger equation for nuclear wave function, and here is time dependent, that is getting solution that depends on time. And we do want to speak only about center of such solution. If you will be focusing on the homework, you may use this as a definition of potential energy surface, right? So it is Coulombic internuclear repulsion and eigenstate of electronic part that parametrically depends on interatomic positions. They form together the potential energy surface. Okay, so done with overview, and now focusing on new stuff. So I do have question to those of you who spend time in details of physics, who like taking physics courses or have physics major. If you do want to practice classical mechanics for like point charges, one can formulate Newton's equation of motion that we all assume to write with closed eyes, and if you do not, I'll put it. But other alternatives that solve the same problems with slightly different equations, how would you call them? Lagrangian, and is there anything else?
Hamiltonian.
Yes, good. What are they?
Like what the equations are?
Yeah. How Hamiltonian system of equations look like?
They're partial differential equations.
Lagrangian is kinetic energy minus potential energy. Hamiltonian is kinetic energy plus potential energy.
Okay, but the equation. How do you get equation of motion for like position, momentum, or other variables?
So for, I think for like momentum, you have to take the derivative of the Hamiltonian with respect to like a velocity. Like if you take the derivative of the Hamiltonian with respect to the like velocity in the x direction, you'll get like the x component of the momentum, if I remember correctly.
Okay, so I'm very happy, even if it is not perfectly precise, you are bringing up the right direction of thinking. Again, don't concentrate. If it will be important, I'll repeat. The Newton equation of motion focuses only on position, and there is a second derivative, right? And there is an alternative formulation of the classical mechanics equation of motion, which is has first derivative, but separate equations for position and momentum as two independent variables. They are connected, but there should be two equations, right? Mm-hmm. Okay, so and Kevin brought up this idea. It is blocked here, but at least you see. So there is equation of motion for position and for momentum, and they are coupled. And what is on the right part of the equation depends on Hamiltonian. So these equations are classical, but we can re-obtain them based on our quantum time-dependent general equation based on Ehrenfest theorem. Okay? So we are going to get equations only for average position and average momentum in order to neglect anything else. Why? Because it is not muon, it is like exponential order of times cheaper. So instead, it's hard to imagine how easier it is compared to full quantum consideration. So if stars will come into right order, if we will complete this meeting alive, it will be the last slide. And right now, if you will, you may wake up and look on it. So I'll without keeping intrigue, I'll summarize what you'll get by the end of the meeting, and then the rest will be just technical details. So before today's meeting, we stopped at Born-Oppenheimer separation, and we are having. I want to face the camera. We do have electronic Schrödinger equation for electronic wave function with parametric dependence of eigenstates of energy, and we do have time independent Schrödinger equation for nuclear wave function. Then which can be also reformulated in the time-dependent Schrödinger equation. But then we need for our practical applications much more humble information, only expectation value of position for each interatomic distance. If you do know solution for nuclear wave function, it is expectation value, right? Brian cat of this nuclear wave function. But there is a way to find solution how this expectation value depends on time without following wave function. So it is our main idea. And then we will introduce the force. I don't understand why it is named after Hellman and Feynman and Koch theorem. I think it is just natural idea that force is gradient of potential with sign minus. And it will include the gradient of electronic wave function and gradient of nuclear repulsion. And then if this force is entered into Newton equation of motion, which you recognize now, second derivative of position equals force over mass. Acceleration, if you multiply by mass, acceleration times mass equals force, right? So this is Newton equation of motion that many of you are already practicing when you do molecular dynamics, for example, in hyperchem, force field molecular dynamics, right? So the Newton equation of motion. But this equation, more familiar Newton equation of motion, follows from Hamiltonian style of equation of motion which originates from Ehrenfest theorem. So the time derivative of position depends on momentum, and time dependent momentum change of the momentum depends on force, right? So we just, as soon as we arrive to this equation, we will celebrate completion of the meeting.
I have a question.
Please.
How do we account for charge in this when we have just when we look at the forces? 'Cause
I should apologize that I didn't create works yet, but if I can find a minute to do it, I will check if you identified charges in the terms for potential energies. Like the part that was named extra credit with lithium, there everywhere when there is a coulombic force between lithium ion or either proton or electron, there is a factor 3 because of charge, right? So internuclear potential energy should be somewhere here and there. It does include information about charge, right?
okay.
And even in the electronic part, when you formulate this potential of electron interacting with nuclei, it also includes the charge of a nuclei, right?
Okay.
So it's it is there. Do not worry.
Okay, sounds good.
That's the Z.
Yes.
Yeah.
Yeah. Well, there is no common notation. We can establish common notation in the room, but some people call charge Z, some people call it Q, some people call it C because of charge. Well, I vote for Z.
Okay.
Any questions? This is the, well, I have many slides after this, but last slide will reproduce this one.
So you just took the partial derivative of what it looks like the transition box. So right under that is the Hellman-Feynman theorem. So you just took the partial derivative of that?
Well, one needs to take expectation value of Hamiltonian in electronic wave functions, apply partial derivative, and through some manipulations, one sees that one needs to, one can move derivative inside the Bryant cap.
Okay.
But there are some tricks with commutation of operators that people devoted to physics will love, and people who are not like focusing on physics will hate. And I'll just skim through showing them. But those are technical details. And again, and we are arriving to the end point of the first chapter. Like we are about to come to the 25% completion of the course. So we are arriving to equations which we will actually solve. Right now we were simplifying, and now there are actual equations. So for electronic part, it will be time independent. This, and for nuclears, it will be Newton equation. So when we meet next time on Tuesday, we will look how to use this Newton equation for optimizing geometry. Yes.
So yeah, you're just bringing them together or in right now, but it's not like we derived them from the Hellman-Feynman theorem.
I'm going to show where it comes from.
Okay, perfect.
Go through steps.
I was just making sure that
Yep.
we were
That's
missing.
summarizing, and this is a typical starting point for computational chemistry, especially in simplified text. So everything we did before was like solid background, so that we have fundamental rock strong. So actual computational chemistry will start on Tuesday. Today we are completing the fundamentals.
Mhm.
Okay. Nothing interesting here. This is just a movie from previous years when goes through optimization. And actually, all we do is related to real life. We optimize geometries and run molecular dynamics. This is done in Avogadro, and here are the alive snapshots of each step. But when you practiced Gauss-U, it goes so quick, and it is typically done on cluster. You see on the output. But this information, how things are optimizing, is saved. And there are ways to visualize a sequence of snapshots. I just put this slide to encourage those who feel discouraged with too many equations. So equations are not for torturing us. They are helping to arrive to real problems. Okay, and it's just a text, you can skip it. But if we practice, if you already have two sets of equation, Schrödinger equation for electronic part and Newtonian for nuclear, we do need, in order to make connection between them, in order to solve Newton equation of motion for atomic positions, we need to know forces between all atoms at each interatomic distance, at each step of our either optimization or molecular dynamics. Where we get these forces? By solving Schrödinger equation for electronic part. And if doing it meticulously, it will be so much easier than everything we hypothesized before, but still expensive. But there are ways that we discussed at the end of last meeting to tabulate interatomic forces based on some training set of small molecules, and then just use parameters for interatomic forces and quickly solve them without recomputing electronic part. Oh, you were waiting for you and trying to. Is Gage coming?
He left.
Oh, he doesn't report to you.
Yeah, he doesn't report to me.
So we were giving you and Gage credit for solving time-dependent Schrödinger equation. We needed your experience and confirming that it is possible. So there is a little homework and a couple of handouts for reading. So in actual calculation, one needs to update ionic positions, solve electronic equation, find the eigenenergy, plug it into potential energy surface together with nuclear repulsion, and then based on potential energy surface goes up, solve Newton equation of motion, get new position, and repeat the cycle. We will go through the cycle again and again with more details. It's just an overview of what to expect. So there should be some details. Again, right now we had a nice discussion. From the discussion, I believe you already got main message of today's meeting, right? And now I'm going back to boring details. If they're boring, again, relax. Do not focus. I'll give you a sign when to concentrate once again. So the potential energy surfaces near equilibrium look like harmonic potentials. Eigenstates there look like this Hermitian polynomials times exponentials. And if you are starting from non-equilibrium Gaussian distribution, one can see how it will evolve in time and it will be momentum, initial position, telling where it will move. But we are going to think of this distribution as infinitely sharp one. So the width of the stuff, like 1 over this d square, is assumed approaching 0, and then the whole this distribution can be interpreted as delta function centered at the equilibrium, not equilibrium, at the current value, expectation value of the position, right?
So which part of that integral is the delta function again?
Everything.
Okay.
We will represent the answer as delta function.
All right.
And here I'm just bringing once again the equations that you are already familiar with. So the electronic Hamiltonian generates eigenenergies, which parametrically depend on position, and they are used to define potential energy surface. Okay, so now we are coming to the actual idea of transition, of the limiting transition from quantum wave packets into point charges. So the credit as now I have at least one supporter who is well, maybe more, who are recently refreshed this stuff in their memories. So the credit goes to Heisenberg for Heisenberg equation of motion, and to Ehrenfest due to his theorem. So the idea is that in case we do not need too much additional information stored in the wave function, if we need only expectation value, then there is a standard way to find expectation value just by convoluting wave function with operator, or one can derive an equation for this observable, for this expectation value. And it is what actually stays behind Ehrenfest theory. So generally, it's not yet Ehrenfest, it's Heisenberg. The time dependence of expectation value of operator is, so here we just apply derivative. First, second, and third terms. Then we drop the last one and take the idea that this time derivative of ket vector is normal Schrödinger equation, and time derivative of bra vector is what? Like time inversion.
Conjugate?
Yeah, conjugate. Or one can interpret, see, if one just changes sign here, so it will be the same as we propagate backwards in time, traveling backwards. And then if one plugs in these two things here and there, one is getting a equation, right?
So we throw out the third term because observables don't change in time, right?
Yeah, we do not have, we neglect explicit dependence of operator on time.
All right.
It's complicated without it. So what is this equation? Again, this is for your entertainment. It will never be part of any exams. and all equations will be solved by computers for us. It's just for curiosity and making bridges between things. So expectation value of operator, and in our situation it will be position, is time derivative of expectation. It's time propagation. Is expectation value of commutation of this operator with Hamiltonian. So one needs to do this commutation operation, which needs a little operator algebra, and then it builds equation of motion which is as good as classical. There will be really, instead of continuously distributed wave functions, it will be like a number, a variable that may change in time. This is really, really good. And it's written A, but we will apply it to P, to R and P, position and operator. Okay, let me try to practice a little. So if A equals R, d R dt I h bar. So what goes first, H, A, or AH? It doesn't matter. We can fix it by minus sign. So
H? Oh.
Okay. So do you enjoy this notation? Do you please lift hands if you have general idea what comes next? Okay. 3.
So where does this equation come from again? This came from the last slide.
Yes. So commute operator R with Hamiltonian. So it is very general. It is a replacement of Schrödinger equation by Heisenberg equation of motion.
All right.
Okay. And then we need to commute, to multiply Hamiltonian by position and position by Hamiltonian. So Hamiltonian is kinetic plus potential. And potential does depend on position. Therefore, the terms T R V R R T R V. So the terms that depend on the same variable as polynomials will drop. And we have only two terms, kinetic energy and position. So the kinetic energy is p squared over 2m r minus r p squared over 2m. Can you say that this is 0? What should it be equal to? Again, I don't care for this class. I'll show you on the next slide. But if you were or will be exposed to like physical chemistry, it's a good thing to recall one day.
Would it be 1? Oh, I was thinking multiply.
Did any of you try to work as substitute teacher in high school? Or I did. So good problems set up for high school should make easy grading, and you should set up problems that they have answers either 0 or 1. From this point of view, yes, it should be close to 1. Well, if you put PR minus RP, it will be constant, like Planck constant times imaginary unit. But here it will be this Planck constant imaginary unit times p once again. So basically it will give you momentum, but we can work out the details, like 1/2m p r minus r p p. So if we swap the order of P and R, there will be penalty for this. And then we will swap order once again to have the same order of operators. So when you practice operator algebra, you may want to keep the same order. And I'll play lazy. I'll do it once, well, more than once. So when you swap order of this R and P, the penalty for the swap is this commutation of R and P, which is Planck constant. And this is, again, it doesn't matter for this class, but if for like quantum physics and physical chemistry, there are two things, only two things that one needs to memorize. The rest is derived from them. One is explicit equation for momentum operator, right? Minus I h bar derivative over position. And another is commutation between position and momentum, right? So if you look from some quantum texts, it will pop up. The penalty for swapping order. Here it was RP, here is PR. But as a price for it, you add IH bar. And then you have this penalty term, and then PPR minus PRP. If we are fans of operator algebra, we are not happy. It should be same order, PPR in all terms. First momentum, then position. So these two operators need to be swapped once again. And we know this. We know this trick, we did it just in previous line. If you swap them, there is a penalty. You add IH bar, right? So the penalty is like traffic ticket. So you get traffic ticket once, and we get traffic ticket second time. So we have minus IH bar P times 2. Okay? We gain 2 traffic tickets. And then the remaining terms are in the right order, PPR, PPR. And then when the order is the same, you can cancel them.
I have a question.
Please.
How are we defining A, and how are we, I know R is our position. Like, are you saying, what is A in this case? Like A is equal to R.
Yes, correct.
So what is A? I guess I'm trying to understand that.
A is arbitrary operator. So the Heisenberg equation of motion will work for any arbitrary operator. Some people use letter O for operator. But if you use letter A, you can tell that Heisenberg is haha equation.
Got it.
Okay, and then when they cancel, you have minus IH bar P, and then there is up front there is a factor 1/2m. So 2 will cancel, and then there will be IH bar P over 2m. P, and there is an expectation value, so these brackets, angular brackets, mean what?
Expectation value.
Expectation value, yeah. And then it was d dt of r. And I'm not competing for highest grade because I always miss the sign here. But the idea is that time derivative of position depends on expectation value of momentum. And I think it is minus. And from Heisenberg Haha equation, h bar comes first as a factor, and h bar and cancels, and I times I will be -1, and then minus will also cancel, so it will be ddt of r will be equal to p over m. So by now we have reconstructed what?
How about the minus sign? There we go.
No, I think I did good. I like making mistakes, but here it was not the case. So here is the minus.
Yeah.
Here is I times I will be -1.
Okay.
And this minus times -1 will be plus. So how do we interpret this equation? Momentum, what is momentum?
Mass times velocity.
Mass times velocity. What is momentum divided by mass?
Velocity.
Velocity. So time derivative of position is velocity. So we did a great discovery. Time derivative of position is velocity, right? But it is we didn't start from like first, second, third Newton laws. We started everything from time-dependent Schrödinger equation and Heisenberg equation of motion, right? So it's quantum. In some sense, it's quantum equation for expectation value. We do need to see how position changes in time. But can we solve this equation only? No, because we do not know how momentum depends on time. And it is typical way. We need to set up equation of motion for expectation value of momentum, right? How are we doing in time? Okay. I will have an excuse to write less and go quickly over slides.
I have a question.
Please, please.
Could you explain the expectation value in a little more detail? Like, is it coming from statistics? How are we looking at this kind of like in a...
There are two types of expectation values. One, statistical average, when you have many samples, and another is quantum average. So quantum average originates from the fact that wave function is distributed.
Mm-hmm.
And then you want to find, if you perform measurement several times with the same wave function, you may get different answers. But if you average over all of these measurements, you'll get expectation value.
Got it. Okay.
And there are tricks to write down equation of motion for expectation value only.
Okay.
What we just practiced.
Okay.
So, commutation, Haha equation, our great discovery. Now we may want to practice it for the momentum, because it will be coupled equations. Position depends on momentum, momentum depends on position. So we practice it again. Momentum commutes with Hamiltonian. Kinetic energy in the Hamiltonian depends on momentum. It will be like p squared. Powers of the same variable commute with each other without any traces. Give 0. Therefore, we remove it. And we write down commutation only between momentum and potential energy. So, when we, again, let me show it. And I'll try to do it quick so that we do not stay too long. Next couple of slides could be very pleasant for PEM, because I skipped the slides from PChem to save time. So when we commute momentum and potential energy, we are recalling one of the two most important equations from quantum field, the definition of momentum operator, right? And we plug it here. So commutation means that you write it in regular order once, then you write minus and you swap the order. Right? And instead of p, we are putting this time derivative over position. If you do it this way, there will be a couple of terms. So first we have derivative, and I'm keeping all constants outside of the brackets. Do not focus, do not listen, keep relaxing. Those are technical details. You'll just arrive to the yellowish summary very soon. So, derivative in front of potential energy. But by rule of derivative of a product, it will apply both to potential and to cat wave function. So you see these two arrows. So it will be derivative of, should be facing camera, derivative of the potential and derivative of the cat wave function. When you look for the second term, you flip the order. Potential goes first, derivative goes second. And now this derivative applies from left to right, only to the wave function. And it will be only one term. So here it generates two terms, here it gets one. And then we add together this plus this minus this. This plus this minus this. So the terms where derivative is applied to cat wave function cancels. And we have a term where derivative is applied to potential only. Through many years, I do not understand why it is named as a theorem, but people call it Hellman-Feynman theorem. Number of letters is even larger than derivation.
So wait, so why do we apply the derivative with respect to R to both the U and the chi term?
Yes. Why?
Yeah, why do we apply it to both of them and not just the U?
Chi is a nuclear wave function.
Okay.
It does depend on position. Mm-hmm. So if you practice just basic calculus, so potential is a function of position, and chi is also a function of position.
All right.
Derivative acts from left to right by convention. So everything that stays here must be treated with this derivative.
Oh, so we're just applying the product rule of calculus.
Correct.
To this. Okay.
Yes.
All right.
Yes. Yes.
Thank you.
So we are getting only this term, and if you carefully plug in all constants, then we will obtain that Planck constant will cancel, imaginary unit will cancel, and then the time derivative of expectation value of momentum will be equal to expectation value of the force, right? Gradient of potential is force. But it is not derivative outside, derivative is inside, between this bracket. And now, when we match together equation of motion for momentum and a couple of slides before equation of motion for expectation of position, we have a closed set of equations. And here, I think it is not right notation. The bracket should be outside. Yes. So these two equations are solved together. And if you solve them numerically, at each time step you do little increment of position, and then position updates your forces, and then you do little increment of momentum. Then you plug it in, and you propagate it together. So this transition from quantum equations to equations that look very much like classical equations is named after Ehrenfest theorems. So we are so rich in theorems.
And this is a basis for the molecular dynamics, right?
Yes, yes.
Okay.
You have a chance to get your work on molecular dynamics published even if you don't care about this stuff and you do not mention. But if you do mention what you approximate and what you neglect and what you keep, your chances increase. So
Excellent.
you have some cynic
Wait,
motivation.
so deriving these two equations, is that the whole point of today's lecture, or is there more?
No. Now I'm going to jump back to the summary slide.
Okay.
But if you apply second derivative to first equation, it will be second derivative of position and equal to first derivative of momentum. But first derivative of momentum can be replaced by force. And then you'll recover Newton's equation, right? So you propagate them simultaneously, going to next time step, or you convert them into Newton equation. So if you have completed it, then we arrive to our summary slide. So in the next lecture we will start actual computational chemistry. Right now it was solid background. So we started from molecular Hamiltonian and reduced it to system of equations that can be solved. This is something that because we know how to solve Newton equation, and there are some tricks to solve the electronic part. Good.
Right. So when we write our paper, this is kind of where we'll put like the Helm and Feynman theorem provides this. This is what we get from it, and this is how we can use to describe our system. So just a little just touch of the background that can describe our system. So this is what the take home for today, I think, is.
Yes, correct.
Yep.
So we are not going to derive new equations and rediscover theories, but we are going to do some practical things. But we will use this background in two aspects. To explain what we do in the legitimate way, and second, to fight with reviewers who sometimes are aggressive, so that we will answer in the right language if reviewers have some critical points.
Right.
Okay. And when we will meet on Tuesday, we will do things that probably will melt the heart of Kurt. Maybe. I don't know how computer sciences are taught now, but many years ago, instead of writing codes, people were doing flowcharts. With like forking. We will do the same for optimization.
Yay!
Okay, and my favorite slide. So, meeting is done. I'll stay here to answer questions if any, but you're welcome to depart and have a nice Friday and nice weekend.
If one of the guys from CPM could grab whatever was handed out today.
Oh, another set of handouts, yes. Thank you.
Thanks, guys!
Thank you.
You gonna end it?
You guys better stay warm out there.
No. Right. See you tomorrow, Mary.
Alright, I'm out of here, guys. Peace. Have a great night.
I consider replacing my boiler with a small nuclear reactor.
I didn't do that one.